Now, the one issue you will have had to have been in lectures or whatever to see how you write this as two first orders. Now, if you do go into your notes, you will find kind of questions kind of leading you there and hopefully figure it out. It will be done in the labs if you're there, but I can't kind of easily do it here in the video just like this. If a number of students have an issue with it, I'll do a third video kind of explaining how to do it. Okay. So I'm going to finish this off fairly quickly. We're going down to a time of 5 here. And now we're doing two Euler's methods. So the derivative of x, this is the easy one, is v. Derivative of x is v. And you might say, well, what? Well, yeah, the derivative of displacement is velocity. So my previous slope, the slope of x, is v. Now, if you differentiate both sides of this with respect to t, you'll get that the second derivative of x is dv dt. So this is actually dv dt. This is v. And then you can solve that as like an algebra equation for dv dt, and you get that the derivative of v, if I'm looking at it right, should be minus 5v minus 6x divided by 2. Now, of course, v and x is no good. So v is the previous slope, so it's the previous v times previous v, and then times previous x. So as I said, I said I wouldn't do this. Differentiate both sides with respect to t. You get the second derivative of x is dv dt. Sub that in there, you get 2 dv dt plus 5v plus 6x equals 0. Solve it for dv dt, you get this. And then we can do our smart drag. This time, the v isn't like a predictor as such. You are interested in the velocity as well, so we can plot this. And there we go. We can see this thing is actually, because it slams as such, this one is underdamped. And you get oscillations, the small oscillations. Okay, so that's the first one. Well done. There we go. X of 2. We'll just double check it. Looking good. Yeah. Right. Now we're going to repeat the same thing. The only thing is our derivative now will depend on m, lambda, and k. So again, you differentiate both sides with respect to t. So the second derivative of x is the first derivative of v. So this is dv. This thing here is dv dt. This is v. This is x. You'll be able to solve for this thing. Right. So off we go. So I'm doing this stuff. So my variables. Okay. So I've got dim x as double, dim v as double, dim t. They're the most important variables that come from the problem. Next are kind of h is coming from the method, and the final time, I guess, is related to the method as well. Then the problem parameters, you've got lambda as double, m as double, k as double, and finally, I'm doing R as integer. I think I'm going to change it to long. I think it's better. Okay, I might do a pause and just do Google long versus integer. So it says that they're always find our own numbers long. So look, it's amazing. I learn new things every year. I've always used row and it was never an issue, but a few students had issues with over 32,000 rows, so you should use long. It says 65,000 rows. I think you can even go longer. So anyway, do it as a long. If you're using integer, you should be fine. Okay, the initial values. So I need my sheet open to see where a lot of these are coming from. So I go in the same order. Dim x, idiot. Cells x is row 2, column 6. V is cells row 2, column 7, because it's the next one. Next up is time. Time is easy, that's just 0. And next one up, I'm looking up here, h. H equals cells. It's next one over. H is the 8th letter of the alphabet. And next one, TF, is equal to cells to 9. I must do my macro recorder as well. Lambda equal, I just call it lam, equals, an option explicit would help you there if I wrote lambda by accident, to 10. I'm just going to look at my dashboard now, so I have m and k to go. M equals cells to 11, k equals cells to 12, and my row or is going to start at 2. Okay. Yeah, all good. Well, I may as well do my macro recorders on here. Macro 1. Select those 3, delete, and the labels again, TXV. stop recording. I'm going to put it up here, called macro 1. Great. Now our loop. So what we're going to do, the stuff we're going to do is some printing. So I'm going to do cells, row given by the row counter, column 1 equal to t. Cells row 2 equal to x. Cells row 3 equal to v. Okay. Now we'll have to be clever down here, right? And there's various different options. So I'm going to pick a particular thing, but there are other. We may as well just go back to it. So look at the warning on page 147. So the thing is that our derivative of v depends on x. And if we calculate the next x before the next v, we get a problem. And if we do it the other way around, we get a problem. So we have this swap is not an option. One of them you can do, and it's the one I do, to be honest. You can call a previous value from the printing you just did, or you could do a previous x or previous v, and before you calculate, say, the next x, you do x previous equal to x, or a runga kutta style, where you might have variables, for example, dv, dt, and dx, dt, which is nice. Now, we're going to probably be skipping the actual runga kutta stuff, so I think I'd probably recommend B or C, but some people are already doing runga kutta style where they calculate slopes first. It's nice. Yeah, so I think I'm just going to go off the worksheet, to be honest. Okay. So, where are we? So, say the next t. The next t is easy. T is equal to t plus h. And if I try and do the next x, x is equal to x, previous x plus step size times the derivative of x is v. And now the problem is, now x is the next x. So I'm going to get the previous x from here. Okay, now if we do our v, v is equal to v plus step size, and now our derivative of v looks like something like minus lambda times v minus k times x all divided by n. This won't work because it's using the next x, so I'm going to take the previous x from here. One option of doing it. I also need to put my row number up, and I'm going to loop until the time maybe is bigger than the final time. Plus h. Okay. So this looks pretty good. Maybe I get an error. We'll give it a go. Looks all good. Insert my graph. I'm going to go through just a few of the things in the notes stuff, so now I can use my program without looking at that. So in terms of the assessment, that's how far. We're going to go into Hein, but I think for the assessment, second assessment, that'll be good. Okay, run the program with h is 0.1, final time is 5, mass is 1, lambda is 2, k is 17, initial v is 0. Okay, run this. So what type of damping? So this is like if you have oscillations, there's not enough damping to stop the oscillations. If it was a door, the door would slam. This first one is underdamped. Now let's go again with a mass of 1, k of 6, lambda of 7. Everything else the same. What type of damping is this? This is over damping. See the way it's taking so long to go to 0? This is like a door that kind of closes quickly and then kind of slowly. This second one is over damped. Now consider m equal to 1 and k equal to 4. What value of lambda gives critical damping? So you can kind of play around a little bit here. So like you go to lambda equal, we're trying to get critical damping. That's underdamped. Who says it has to be a whole value? But anyway, this is still underdamped. I go to 3. That's still underdamped. There's still oscillations. I go to 4. This looks quite good. Now, if you actually go smaller than 4, you will see the nearest oscillation. It's not really clear, but the x does go negative. If you go a bit bigger, you'll see it taking longer. The value is 4, and you can tell yourself that's right by considering stuff you do in Marina's class. Okay, so I think we said this. Yeah, okay. Now, going into Hein's method. So, I guess we'll do our... so that's the main part done, but we'll keep going. So macro 2 this time, delete, oh, I missed steps, I'll go again. Actually, there's no need to print the predictor here, really, it's just going to complicate things. Macro 3, we go again. Delete txv stop, that was macro 3. Yeah, I could be lazy, but and copy paste that, but I don't think it's the right thing to do. I think you should practice. So define variables, do all these. Dim x as double, dim xb as double, dim v as double, dim v predictor as double. Let's be very careful here now. Dim t as double, dim h as double. I'm actually going to stop to make the note about long versus integer for the row. Dim tf as double, dim lam as double, dim m as double, dim k as double, and dim r as long, but integer should be okay. Now we're going to give all of them initial values. Now maybe something that's kind of middling lazy would be to say, well, look, you have all the variables here. If I copy paste them, I'm not going to miss any. So I go on x equal to cells 2, it's in f is 6. The predictor is unique, they don't have initial value. V equals cells 2, 7. The predictor does not have initial value. T equals 0, it's in the dashboard. H equals cells 2, 8. This isn't actually that clever way of doing it at all, it's kind of dumb. TF is equal to cells, it's the next one, 2, 9. Lam equals cells 2, 10. M equals to cells 2, 11. K equals cells 2, 12. And then R is equal to 2. And now my loop. So do, again, the stuff is the same. It's cells row counter column 1 equal to T, cells row counter column 2 equal to X, cells row counter 3 equal to V. And now things get a bit more interesting because here we have the predictors as well. So we should do the predictors first. I think one part of it is actually not too bad because we can do X predictor is equal to, now if you look at the Hines method, the predictor doesn't jump off the predictor, it jumps off the good one, plus h times, and the derivative of this should be the previous one, and the good value, not the predictor, v. Yeah, I think you see the problem we had initially won't be so bad here. V predictor is equal to v plus h times, now the derivative here is minus lambda times v, minus k times x all over m. Okay, not too bad. Now we do the rest of these yolks. So t isn't too bad, t plus h, x isn't too bad, x plus h times, oh yeah, and of course we're not doing Euler's method, we're doing Hines method. So rather than the 1 dx dt, we have 2 dx dt's averaged. One is the previous dx dt and one is the predicted one. And then v is equal to v plus h times, now we're going to average two slopes. They both look like this. So I'm going to copy paste this. So that's going to be the previous one plus the predicted one. Make this big. Hey, come on. So this is the previous v, no problem. This is supposed to be the previous x, but after this line, this is now the next x. So it should be the previous x. So you can have an x previous, you can do Runge color style. I'm going to use the printed version. Then this should be v predictor, because this is the predicted next slope, and this should be x predictor. And that's pretty much just done. We want to loop until the time is bigger than the final time plus h, and that's our Hines method done. Hopefully not too scary. And we'll run it there. And things, someone's a dumbass. I forgot to put my counter up. Or I go up this one. This will be more accurate than what we did previously. We don't need to print the predictors. Right. There's that. I don't know, is there any questions on this? Yeah, I'm not sure these are the same questions we had, so they probably should have been deleted. I'm going to make a note of that. Okay, those who are a bit concerned about Hoyne's method, I think I have these down as doing Hoyne's method. I think probably what I'd advise people to do, considering this lab is done the week before the lab with Hoyne, is to try it. Yeah, I think actually people should push themselves to Hoyne, to be honest. But if you're doing this lab again after the first assessment, which is possible, you could just do Euler. So we're going to do what's it called? Hoyne's method here. Okay. So I got some variables to go here. I have dim x as double. This is van der Waals oscillator. What it is, we'll see it in lectures. P is double. Dim v is double. Dim vp is double. T is double. Dim h as double. You get cool graphs of this, y'all. I don't fully understand. We'll talk about it a little bit in lectures. Tf is double. U is the one parameter. It's like a damping coefficient. Is double. And dim r as long. Initial values. Okay, so I'll take some from here. Using initial x of 1, initial v of 0. Look at that math graph. V 0, mu equal to 2, h equal to 0.1, final time 20. Right, let's go back. Initial values. So x is up there. X equal to cells. E is the 5th letter of the alphabet. X predictor does not need initial value. Dim v, no, dim v. I'm tired. Cells to 6. VP doesn't t equal 0. Dim h cells to 8. TF equals cells to 9. Mu equals cells to 7. Right, and then the loop, the stuff, so we're going to print cells row 1. Someone didn't give all the variables their initial values, or equal to 2. You can see this is similar. Okay, T cells or 2 equal to X cells or 3 equal to V, and then calculate the next T. So next T is easy, and I will forget about the R again, so I'm going to do it now. R equal to R plus 1. T equal to T plus H. Now we threw the two predictors, and actually we probably should even do them before the time. Okay, so the x predictor is easy. Previous x plus step size times the slope of x is v. The v derivative is harder. V is equal to v plus step size times what should be dv dt. Now what I'm going to do is I'm going to pause the video and see have I the derivative written down anywhere in the manual. Okay, it's not written down fully, but we have this. So the derivative of v, what you do here is you let v be dx dt, or dx dt equal v. So the derivative of x is v. We saw that a few times now. And then differentiate both sides. This is actually dv dt. So dv dt, add this to both sides, is plus mu. Try and write this in. So dv dt, if you do this, is plus mu. I don't need to write the plus. So it's mu times 1 minus x squared times v, and then you take away that x. So that's the derivative. You get this weird thing sometimes with the squaring. You have to put a space around the power. I don't know. So that's the derivative of v. That'll make more sense after lectures. Okay, so now we have to do the next x using Hoyne is equal to previous plus step size times the slope of x is v. So previous plus predicted divided by 2. And now we're going to have two of these slopes for the Hoyne's method for v. So v is equal to v plus step size times previous plus predicted next, average them out. So this should be the predicted. So you might be able to see that. Predicted x, predicted v, predicted x. This here should be the previous x, but now after this line, x is now next x. And so while this v is okay, these two x's aren't. So I could take a previous x from the printed one. And this is where the advice comes from to up the row last. Okay. So and then loop until time is bigger than final time. Now this has gone now to over 20 minutes, so I'm tempted to leave it and not do the pendulum, but if anyone has an issue, come back and I'll send me on your file and we'll have a look. So hopefully this works. I'm not sure if it will or not. User type not defined. I don't know. I'm still stuck in this, I think. We'll go again. There we go. And we should get a really cool graph. We'll learn a little bit about this van der Waals later in class. Okay, so that's that. So in the assessment, you wouldn't have the predictors. You just use one previous slope, but just while you're doing this, before the first VBA assessment, you should use Heinz method, I guess.